Hello and welcome to NCC Group's Cryptopals guided tour. My name is Eli, I'll be your guide. In this video we'll be looking at Challenge 14 from Set 2, which is a follow-up to Challenge 12 with a slightly more complex setup. In Challenge 12 we used an attacker-controlled prefix to recover a secret suffix. This time we don't get to control the prefix. In fact, our input isn't a prefix or a suffix, it just gets placed in the middle of the plaintext with an oracle-chosen prefix and suffix. And we have no idea how long these oracle-chosen fields are, at least to start. But we do have one thing going for us, which is that these fields are fixed, meaning that we can trust that their lengths won't vary between calls to the oracle, and neither will their contents. So the goal then is the same as in Challenge 12, we just recover the secret suffix. We don't need to recover the prefix, we just need to work around it. Well, alright then, how might we do that? What's the plan? Well, the setup, if you recall, is similar to our ECB CBC detection oracle. That was another challenge with a random prefix, although that one had variable length. And in that case, we just padded out the first block of the plaintext and ignored the first block of the corresponding ciphertext. So we might think about applying the same idea here. The setup is slightly different though. The length of the random prefix is fixed, but we don't know what it is. We don't actually even know what range it might fall into. Although as a technicality, since we will be implementing this oracle, we can choose that range. But it would be more honest of us not to bake that knowledge into our code and to write a solution that works for any length. So the first step is to figure out how long the prefix is. We know that the prefix ends as soon as our chosen message begins, so let's try to solve the related problem of figuring out where our message is being placed in the plaintext buffer. We can start by sending two different one-character messages to the oracle and diffing the resulting ciphertexts. And did you catch that? The second block of the ciphertext changed. So our message byte must be getting placed in the second block of the plaintext. Now how do we narrow this down? This is, in my opinion, a clever challenge with a really satisfying solution, so I'd really recommend you pause the video and take some time to think about this. I think that if you do figure it out, you'll be glad you took the time, and if you don't figure it out, well, you might still be glad because at least you tried, which is better than nothing, which is what you would be doing if you don't try at all. And on that note, I'll wait for a moment. Okay, now let's continue. The crucial idea here is to move our differing bytes within the plaintext, to shift them forward until we see a different block changing. If we prepend a null byte to each of these messages, we see that, again, the second block of each ciphertext changes, and that the resulting blocks differ. So we know that the second block of the plaintexts must differ as well, but where do they differ? Is it in the same place as before? Clearly not, because the first byte of each of these messages is equal, so the plaintext's first message byte must be equal as well. And so the plaintexts must differ in the second message byte instead. Now, if we keep repeating this process, we'll keep moving the point of divergence further into the plaintext, and eventually we'll reach a point where the second blocks of these ciphertexts are equal. And as soon as this happens, we know exactly where the plaintexts are diverging. It must be in the first byte of the third block. This is a big step forward. Now we know one plaintext byte, and we can work backwards from here. We can figure out exactly how far into the previous block our message's prefix extends. And from there, the length of the oracle prefix follows trivially, because it must fill up all the space up until our message. After the message, we have the secret suffix, followed by the padding bytes, which we can now figure out in the usual way, the same as in Challenge 12. In fact, if we were paying attention during our search earlier, we might have noticed the point at which the ciphertext length ticked up. That's not guaranteed to happen during this search, but of course it can happen. And if it doesn't happen, we can keep adding message bytes until it happens. At which point we can deduce the length of the message minus padding, just like we did in Challenge 12, and we can use that to get the length of the secret suffix, which lets us reconstruct the padding as well, and just like that we have the entire plaintext mapped out. At this point we know exactly what we're dealing with in terms of prefix bytes, and we also know exactly how to compensate for it. In fact, we could even, if we wanted to, write a wrapper around our oracle to compensate for the prefix. More on that in the screencast. And with that prefix out of the way, the rest of the attack can proceed exactly like it did in Challenge 12. So let's try writing it out. Alright, let's get to it. This is going to be a fun one. Now this is going to look a lot like Challenge 12, and in fact, the interesting thing about this is going to be figuring out how we can reuse parts of Challenge 12 in this new context. So let's start out with discovering the prefix length, because that's what's different about this challenge. And we discussed how we would do that, so it's fairly easy to go ahead and just implement what we discussed. Although right off the bat, if we want to do our type signatures right, we're going to need to import this ECB oracle type value. And let's just get ourselves a couple ciphertexts to start from here. And you recall that the idea is basically to take these two and then prepend equal bytes to both of them. until we notice that the shared prefix of the ciphertext extends in length, at which point we will know that these diverging bytes are in the first byte of the first diverging block of the ciphertext, or the plaintext corresponding to that ciphertext, I should say. But we can actually optimize this a bit further, because we already know that we're going to add no more than 16 null bytes. So in the case of the all null ciphertext, let's just start it at the finish line, and then we can just update this one to catch up with it. And that'll save us a bunch of queries to the Oracle. This is just a slight optimization over what we talked about in the animation, but it's the same idea. Oh yeah, and common prefix, check this out. This is another weird thing about Python. There is a built-in for finding the length of the common prefix between two strings, but it's from os.path, because I guess the idea is that this is useful when you're working with, directories and paths, but it's also useful in tons of other contexts. So it's a funny place to put it, in my opinion, but there it is. So we take the length of that, divide it by the block size, and we're doing integer division here, and that gives us the number of blocks that are equal between these two. And then we can get the index. This is going to be the index of where this diverging byte is going to be once we've added enough null bytes in front of it to extend the length of the shared prefix. Equivalently, it's also going to be the index that we slice up to get that shared prefix. I'm not sure if this is making any sense, but it'll be clearer once I write out the code. So now we are, generating some number of prefix null bytes, and it's going to range from 1 to 16 inclusive. And then we're prepending those to this, which is, the same as up here. And that will give us a new ciphertext. And we're going to check whether that ciphertext has a longer shared prefix with CT1 than CT2 does. And the way we're going to check that is by slicing them both up to index, which of course is one block further than the number of shared blocks that they have to start out with. And if that happens, once this condition is met, we know that the index of this byte is equivalent to the length of the prefix plus the leading null bytes. And so if we subtract the length of those, then we get the length of the prefix. And this should never happen, of course, so let's just throw an exception if it does. And now, for the other little bit of magic here, this is something that I think is quite fun. So something that you see a lot in formal crypto proofs, and in other areas as well, but this is what I want to focus on here, is this idea of using one oracle to create another one. This is something that you do a lot in like proofs of equivalency. You say, if I can solve problem X, I can use that to solve problem Y, and vice versa. Therefore, those two problems are in some sense equally hard. Or you could say, any attack that applies to this one crypto system must also apply to this other one, because given an oracle that conducts the attack, I can use it to attack this other system. You can make arguments of this nature. In this case, I can say, given an oracle that gives me this, and the knowledge of this, I can construct the oracle from challenge 12 that just gives you this. And the way I do that, of course, is by taking the length of this, adding enough bytes to pad this plus the padding bytes out to a full block, and then taking the string passed to the oracle and putting it after those padding bytes. That way I get a ECB ciphertext where the first block is this plus the padding, and then the following blocks are just this, which I actually care about, and then I just drop the first block and return the rest. And that behaves just how this would, because ECB doesn't have any relationships between the blocks. So this is actually surprisingly straightforward and easy to do. And we do want to consider the possibility that the prefix is more than one block long. So this tells us how much padding to add to get to a multiple of the block size. And this tells us how far we will be when we get there. So yeah, I should mention, when I was discussing this, I was assuming that, you could pad this out to one block for simplicity, but it could be multiple blocks. And if it is multiple blocks, then this will still gracefully handle that. And now we're going to define a wrapper. So there we go. And this is fairly straightforward. I mean, it's just adding the padding bytes and then passing the message, and then it's cutting off the ciphertext corresponding to the prefix plus the padding bytes. So this, given this oracle, will produce something that behaves exactly like this oracle. And what that means is that once we run this function to get the prefix length, we can run this function to get an oracle like challenge 12, and then we can reuse our solution code from challenge 12 to solve challenge 14. And this is the point at which I'm kind of kicking myself for deciding not to write a main function, and I made such a big deal of that in the video for challenge 12. I guess I could go back and re-record it, but I'll be honest with you. I'll own my mistakes. I'm going to write a main function here that just takes an oracle and launches the attack on it. Actually, no, it's also going to take the block size and postfix length. And I guess I can annotate this. Oracle is going to be, let me get some more real estate here. This will just return the contents of the plain text. And yes, so all of this we can do outside of the main function, I think. Actually, no, I'll put this in there. But this will happen outside of it. And that's purely just because with our current knowledge of the future, we know that we're going to be computing all this stuff a little bit differently in challenge 14. So let's just make it easy on ourselves and not bake that into main. But everything through like here, I think we can just put up here, right? And actually, truthfully, we can do that. And then we can also have a flag so that we can decide to be fancy and do the Hollywood style printout if we want to. And we don't have to modify the source code to do that. Or at least we don't have to uncomment anything. We would still have to modify the source code down here where we eventually end up calling main. But not to get sidetracked. So let's see. So now we're just going to call pt equals main oracle block size postfix length. And then this should work just as before, I believe. Is the block size even used here? Oh, it's not. Okay, so let's cut that argument out, I guess. And yeah, now the static analysis is not mad at me for any reason, so I'm willing to believe that this is actually valid. Let's run it again, just to make sure it still works. Yes, it does. Oh, I just drove on by. I love that. Why would I stop? Okay. And so now challenge 12 is a little bit more to my liking, and we have this main function that we can reuse. And so now we can write a super, super terse main block in here. We can be like, oh yeah, and we need to import this too. Let's be lazy and do that. Be even lazier and copy over that comment. And there's a slight technicality here, which is that right here, this is the postfix length in challenge 12, but in challenge 14, it's the affix length, which, by the way, is a great little vocabulary term. An affix is a prefix or a postfix or both. So I'm not going to go as far as renaming the function, but I am going to rename the variable there, just as a nod to correctness. And now, after we have that, we can get the prefix length. And given that, we can transform this oracle into the oracle from challenge 12. And there we have it. Let's see if this does the trick. Check it out. It's only like, what, 44 lines, not even a full screen of code. That's the power of code reuse. So I'm not actually going to quit just in case I need to make any changes here, but we'll... Oh, okay, come on. Come on now. Postfix len, okay, yeah, that is affix len. Oh, yeah, so I guess I need to equals affix len minus prefix len. There we go. Yeah, because this is going to be the combined length of the prefix and postfix, and so we need to know the length of each of them on their own. We need to know the prefix length to wrap the oracle, and we need to know the postfix length to run this main attack here. So with that correction made, there it is. And this, as you can see, gives us the exact same result as challenge 12. And I'm quite glad to see that. I hope you enjoyed this one. I hope that maybe you found this interesting or helpful. And I'll see you in the next one.